SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture 21st. In last few lectures, we were discussing about different design approaches for axial flow compressors and fans. So we were discussing about design methods named as a free vortex design, force vortex design, constant reaction design, exponential design, constant alpha 2 and work loading or our fundamental method. Now this is what is a compilation of all design methods what we have discussed in past few lectures. That's what is in sense of the variation of work with the radius, world distribution, axial velocity variation with the radius, variation of degree of reaction, whether this method is opting for or is it satisfying a radial equilibrium, and we will be putting some remarks that's what is related to the final blades what we will be getting. So if we look at very first method what we have discussed, it is free vortex method, and as we have discussed during 50s and 60s, people they were using this method for the development of gas turbine engines, application to aero engines. Okay, now in that what we are looking for is my work variation, that's what will remains constant. I'll be having my world distribution as say R into CW equal to constant, and if we look at this is what it says, axial velocity also we are assuming to be constant, and we have derived with it says my degree of reaction, that's what is varying all the way from hub to tip, and this is what is satisfying our radial equilibrium equation. And if you look at this method, that's what is giving highly twisted blades, and we have realized there may be chances for my degree of reaction to go 0 or maybe negative value when we are looking for free vortex design concept. Okay, in order to overcome what limitations we are having with the free vortex design, we have opted for different approaches. One of them, that's what is a force vortex design approach. We can say my work variation, that's what is varying with the function of R square. Here world distribution we are assuming CW divided by R equal to constant, and if we look at our axial velocity, we are calculating based on radial equilibrium, and it says my degree of reaction, that's what is varying from hub to tip, and yes, this is what is satisfying our radial equilibrium equation. So if you recall from our radial equilibrium requirement, we say we need to have constant work input all the way from hub to shroud. We need to have our axial velocity to be constant and CW into R equal to constant. If we are satisfying these three requirements, then we can say our radial equilibrium it is satisfied. Then we have discussed if we are able to have two parameters, that's what is known to us, we can calculate our third parameter. So that's what we have done in our force vortex design. Then we have started discussing about the constant reaction design. So if we look at, it says my work variation along the radius, that's what is constant. My world distribution, that's what we have arbitrarily chosen, world velocity component, it says my CW1 and CW2, that's what is varying in the form of AR plus or minus B by R. So at the entry we are assuming my world distribution, at the exit we are assuming different world distribution. My axial velocity, that's what we are calculating based on radial equilibrium equation, and as we have decided with say constant reaction, so it says my variation of degree of reaction, that's what is constant. And the limitation with this method, it is not satisfying radial equilibrium, okay, but it says this is what is more logical design, and it may be used for design of special kind of compressors, okay. Then we are having our exponential design method. If we are looking at my work variation, that's what is constant, and my world velocity distribution, we can say that's what is based on my selection of arbitrary world distribution. We can calculate our axial velocity based on radial equilibrium equation, and it says my degree of reaction, that's what is varying along my span or with radius from hub to shroud, and we can say this is what is satisfying my radial equilibrium equation. This also people used to say as a more logical design. So many fans, many compressors in actual engines, we are finding they are having of this kind of design configuration. We have discussed about the variation of my exponent from ranging of say maybe 0.8 to 2, that's what is of special category, and there we are using this kind of design concepts. These days people they started talking about constant alpha 2 design, in which at the exit of my rotor alpha 2 we are assuming to be constant, okay. So there are special requirement downstream of my rotor, we are having stator, and for more challenging designs people they are opting for constant alpha 2 approach. It says my work done supposed to be constant, we can say my world distribution, you can say my CW2, that's what is constant. We are assuming our world component at the exit of rotor to be constant, and at the entry we can assume that to be say A minus B by R. We are having this axial velocity, we can say it's supposed to be constant. We can say my degree of reaction also is around constant, you can say about constant, approximately constant. Here we are ignoring our radial equilibrium. The beauty of this design is we will be having less twisted blades, okay. So recent compressors what we are looking for, say for LP compressor, for HP compressor, even for high bypass ratio fans or for low bypass ratio fans, people they are looking for the special kind of requirements, and this designs that's what will be catering those. Then we were discussing about say work loading or the fundamental method, that's what it says my work done or work, that's what is varying along my radius. We are having variation of my CW component because at all stations we are not assuming our CW at entry and CW at the exit. Basically that's what we are calculating based on our fundamental understanding of aerodynamic work and thermodynamic work. We can say our axial velocity we are assuming to be constant. We will be having degree of reaction, that's what is varying all the way from hub to tip, and in this case also our radial equilibrium we are ignoring. Now the case is what blades we are getting, that's what is having less twisted blade. So it is all the choice of designer to meet special requirements, and based on that he or she will be doing the design, a group of people they are doing their design, and finally based on their expectation, if the design is meeting with, they will be going for finalizing that design approach. So there is no unique method in sense, you are having multiple choice here when you are doing your design, okay. So with this background, let's try to solve a numerical, that's what will be giving you idea how do we approach with say different design concepts. So let's take a numerical. It says a low speed compressor need to be designed to have overall pressure rise of 1000 Pascal with design speed of 2200 rpm. The hub and tip radius are 0.1 meter and 0.2 meter respectively. The axial velocity is 30 meter per second. The estimated stage isentropic efficiency and work done factor, they are 95% and 0.98 respectively. The ambient conditions are P01 equal to 101,325 Pascal and temperature as 288 Kelvin. Calculate the variation of air angles and degree of reaction for free vortex and constant reaction world distribution. So, this is what is a numerical. We can say what all data, that's what is given. We know what is my tip radius, it is 0.2 meter. Hub radius is 0.1 meter. You can say, you can calculate your mid radius, that's what is 0.15 meter. We have our rotational speed as say 2200 rpm. You can say this speed is a low speed compressor. We will be having our efficiency to be 95%, and you can see work done factor, it is given 98%. So, you can say this is what may be the first stage. We are having our entry pressure and entry temperature, and we are expecting our total pressure rise of 1000 Pascal, and axial velocity also is known to us. Now, what all we are looking for is, we are looking for variation of my air angles and degree of reaction. So, you can understand, if we are looking for air angles, we must know what all are the velocities at the entry of my rotor, what are the velocities at the exit of my rotor. When I say velocities, we can say what are my absolute velocities, my relative velocities. Based on that, we will be calculating our CW, that is nothing but my world component, because that's what is important in order to calculate your degree of reaction. Okay, and this CW, that's what you can calculate based on what all work done is given to you. Okay, so in order to meet this requirement, let's move from bottom to top approach. Say initially we will be implementing our work done equation for the calculation of parameters. So here what we know what is my total pressure rise required, we know what is our efficiency, and based on that we can calculate what will be my temperature ratio. Once we will be calculating our temperature ratio, we are able to calculate our thermodynamic work. So let's move step by step. So very first point, it says my stage pressure rise. You can say P02 by P01, you can say what pressure rise we are expecting is say 1000 Pascal. That's what will be giving me my pressure ratio of 1.00986 pressure ratio. Now based on this pressure ratio, we can calculate what will be our temperature ratio. So here this temperature ratio we are correlating in sense of my pressure ratio and efficiency. So these two are known to me. If I'll be putting, that's what will be giving me my temperature ratio as say 1.00298. Now once this temperature ratio is known to us, we can calculate what will be my outlet temperature. So we can say we are able to calculate what will be my delta T0. So here if you look at, since this is what is low speed application, we are expecting our pressure rise in the range of 1000 Pascal. That's why my pressure ratio is lower, and that's the reason why my T02 is also coming to be lower. Okay. Now once we are calculating this T02, we are able to calculate what will be my delta T0. Okay. Now let's try to calculate what all will be my peripheral speed at different stations. So in order to calculate, we can say my peripheral speed at the hub, it is my angular speed into hub radius, my angular speed into say mid radius, my angular speed into tip radius. So this radius at hub, tip and mid section, that's what is given to us. So if you will be putting this, it will be giving me my peripheral speed at different stations. Just understand, we are interested in calculation of what is happening at different stations, mainly at 3 stations: mid section, hub section and tip section. Now here in this case, if you look at, we can say we can correlate our aerodynamic work and thermodynamic work, and based on that, if we are putting this equation, it says my change in whirl component, that's what is a function of Cp delta T0, my work done factor and my peripheral speed at the mid station. So we will be doing our calculation what is happening at the mid section first. So it says my delta Cw, that's what is coming as a 25.33 meter per second. Now what we are asked for? We are asked for implementing 2 different design approaches. First, it is free vortex design, in which we can say my n equal to -1. Okay, so let's try to approach with say first design methodology, that's what is say free vortex method. So here if you look at my delta Cw, that is nothing but the change in my tangential velocity component, we can write down here it is Cw2 minus Cw1. Since we are considering our entry to be axial one, that's the reason why my Cw1 that's coming 0. So if we are putting these numbers, it says we are able to calculate the whirl component at the exit and at the mid station. Okay. Now if we are considering, this is what will be my velocity triangle. Do not forget to plot velocity triangle in order to understand and in order to calculate various angles and various velocity components. So here if you look at, this is what is representing my inlet velocity triangle, this is what is representing my outlet velocity triangle for the rotor. Okay, so from my velocity triangle, I can say my tan beta 1, that's what we can say, it is UMICA. So based on that, this we have calculated, Cm that's what is given, it is 30 meter per second. So based on that, we can calculate what will be my entry air angle, beta 1. In line to that, based on my exit velocity triangle, we can calculate what will be my beta 2. So here this tan beta 2 we can write down, that is nothing but minus Cw2m divided by Ca. This is known to us, Cw2 is known to us, my axial velocity that's what is known to us. We can calculate what is my beta 2 at the mid section. Okay, so you can understand we have calculated what is our whirl component and what will be the change in these angles. Now at the exit, similarly we can calculate what is our absolute flow angle. So if we are putting this, say it says tan alpha 2, that's what is given by Cw2 divided by my Ca. Ca is nothing but this is what is my axial velocity component. So it says I will be having my alpha 2, that is 40.17 degree. Now what all we learn? For free vortex design, we are considering my Cw into R equal to constant. So here in this case, since my Cw at the mid station is known to me and my radius is known to me, so I will be writing, say we can write down Cw2 at tip into R tip, that's what is equal to Cw2 at the mid station into R at the mid station. So you can understand we are basically calculating the constant, and what we have assumed throughout my span, my Cw into R that remains constant. So that's what will be giving us the idea to calculate what is happening in sense of change of CW2 at mid station, at tip and at the hub. So let's calculate what is happening at the tip. It says my CW2 at the tip, it is 19 meter per second. Okay. Now once we are able to calculate our whirl component at the tip, we can calculate what all are the flow angles. So what we know, my alpha 1, that's what is 0 because we are considering axial entry. So based on my velocity triangle, we can calculate my 10 beta 1, that is u by Ca. Do not forget this u is at tip. Okay, and my axial velocity we are assuming to be constant. So u tip, what we have calculated earlier, it is 46.08, and Ca, it is known to us, that's what is 30 meter per second. So based on that, we can calculate our beta 1 at tip, it is 57 degree. Same way we can calculate what is happening with my beta 2 at the tip. So if we are looking at, it says my, from velocity triangle we can write down my 10 beta 2 at tip, it is u tip minus CW2 tip divided by Ca. So that's what is giving my beta 2 tip as 42.07 degree. Okay. Now same way we can calculate what is happening with my absolute flow angle. So that's what is nothing but 10 inverse CW2 by Ca, and that's what is giving alpha 2 as 32.35 degree. Okay. Now, based on what understanding we have, we can do our calculation at the hub station also. What we know from the free vortex concept, my CW into R equal to constant. Since this constant at mid station it's known to me, I can do calculation what is happening at the hub. So I can write down this equation as a CW2 into hub into RH equal to CW2 at mid station and RM. So if we are putting these numbers, it says my CW2 at the hub is coming 38 meter per second. In line to what we have discussed, we can do our calculation for beta 1 at the hub. Here also remember this beta 1 we are calculating at the hub, so you will be having change in your velocity triangle. Do not forget. Okay, so make a habit to plot the velocity triangle. That's what will be giving you indication. Say you are putting your hub u at hub. Okay, and that's what is giving me beta 1 at the hub. Same way we can calculate based on our exit velocity triangle beta 2 at the hub. Okay, and this is what is similar to what we have done calculation at the mid section, in line to what we have done calculation at the tip section. Okay, and this is what will be giving me what is happening in sense of my alpha 2 and what is happening in sense of my beta 2 at the hub station. So if you look at my beta 2, just careful, that's what is coming, minus 26.56. Just look at, say on one side we are putting this beta 2. Okay, so do not get confused that angle is coming negative. Just you need to put that, or you need to represent in such a way that it will be on the other side of my velocity triangle. Okay. Now if you look at my blade or say my aerofoil shape also will be changing accordingly. Okay. Now alpha 2 you can calculate, that's what is coming, 51.7 degree. Now here if you look at, we have done all our calculation for CW1 and CW2 at different stations. We have calculated our flow angles. Now let's move with the next step, that's what is for the calculation of degree of reaction. So my degree of reaction we can write down, it is 1 minus CW2 plus CW1 divided by 2u. Now let's try to put that or rewrite. We can say my peripheral speed at any station, that's what is we are writing as a my peripheral speed at the mid station into this radius ratio. This R is nothing but that's what is representing particular station, and RM, that's what is representing my mid station. Okay. So if we are putting this in the form of formula, it says my degree of reaction we can represent by this form. Let's try to say reformulate that. So this is what will be my degree of reaction. Now what we are looking for is a variation of degree of reaction at different stations. So you can say, we can write down this degree of reaction in a more simplified way. It says degree of reaction, it is given by 1 minus some constant by R square. There is a reason behind calculating. You can straightway do calculation by putting some calculation of say CW2 at hub, CW2 at say hub. You can put CW1 at tip, CW2 at tip. That way also you can do the calculation. But let me simplify this. So it says this constant we are writing as say CW2 into R into Rm divided by 2 into Um. And this is what will be giving me my degree of reaction. That's what is given by 1 minus 0.0082 by R square. So this is nothing but some constant divided by R square. Now this R, as we have discussed, there are different locations. We know what are our radiuses at tip, we know what are our radius at hub and radius at the mid station. So let me write down degree of reaction at mid station, degree of reaction at hub, and my degree of reaction at tip. Let me put all these radius values at mid station, at hub, and at the tip. That's what is giving me the variation of my degree of reaction. So if you look at carefully, it says my degree of reaction at the hub is coming 0.18, at mid station it is coming 0.63, and at tip it is coming around 0.79. So you can say for free vortex design, we will be having the variation of degree of reaction from hub to shroud. Okay. After doing all this calculation, let's move with the second approach. That's what is a constant reaction approach. And for this constant reaction approach, we are assuming our degree of reaction to be constant and constant work addition. Okay. This is what all we know from our previous calculation for say peripheral speed at hub, peripheral speed at mid station, and my peripheral speed at tip station. What we know, our degree of reaction, that's what is given by 1 minus delta Cw by 2U. Now, if we are arranging this term, it says my Cw2 plus Cw1, that's what is given by 2U into 1 minus R. Okay. What we know, we are having this delta Cw term or change of Cw and Cw2 and Cw1. That's what is also coming in my work equation. So let me put my aerodynamic work and thermodynamic work to be same. If we are putting that, it says my Cw2 minus Cw1, that's what we are representing in the form of Cp delta T0 by lambda into U. I'm sure this is what all we have discussed in our class, but this is just for your understanding what all we are working at this moment. Okay, so our requirement, it is to calculate what is my Cw1 and what is my Cw2 at entry and at the exit of my rotor. So if we will be putting, say we are looking for our calculation at the hub station. So we can write down, we are having two equations what we have seen. One, that's what is in sense of degree of reaction. Second, that's what is in sense of my delta T0. So delta T0, that's what is known to me, and this degree of reaction, that's what we are looking for. Okay. So it says if we are assuming say our degree of reaction to be 0.5, that's what is given to you. Say at mid station, or say this is what is at the hub station, it is given, say it is 0.5. If we are considering that, because it's a constant reaction design, it says my degree of reaction to be 0.5. So you can understand at hub my degree of reaction is 0.5. So if I will be putting this in this equation for degree of reaction and my work done equation, where I know all these numbers, if we will be putting this into case, it says my CW1 and CW2 at the hub station we can calculate. And that's what is coming. My CW1 at the hub is minus 7.4 meter per second and my CW2 at the hub is 30.44 meter per second. Now, once this is what is known to you, we can put our velocity triangle. Be careful, we have done our calculation for CW1, and if you look at this CW1, that's what is coming to be negative. Now you are expert enough to make your velocity triangle. Okay, so you can say I am having negative swirl, that's what is coming at the entry. So that's what it says. My beta 1 at the hub, we can calculate it is UH minus CW1H. Since this is what is in negative direction, you can say that's what is getting added up here. This is what is you need to take care of. That's what is giving me my beta 1 at the hub as 45 degree. Same way we can do our calculation for alpha 1, that is coming minus 13.85. Now, what design approach we are discussing? That's what is constant reaction design approach. So what it says, for 50% reaction, we will be having our blades to be symmetrical blade. So for symmetrical blade, what it says, my alpha 2 and beta 1, that's what is same, and my beta 2 and alpha 1, that's what is coming to be same. So you can say my alpha 2 and beta 1, that will be 45 degree, and my beta 2 and alpha 1, that's what is minus 13.85 degree. In line to that, we can do our calculation at the mid station. So we can rewrite the equation and we will be doing our calculation for two different approaches. One, that's what is constant reaction, and my work done equation. We will be getting our CW2 variation at the mid station. We can calculate our CW1 calculation at the mid station. Once this bulk components, that's what we are calculating with, that's what will be giving us idea how to do calculation for variation of our flow angles. So here if you look at, this is what is my beta 1. So beta 1, that's what we are calculating. Just look at here at the mid station, my CW1, that's what is coming positive. So that's what is on the other side. You can see my alpha 1, that's what is coming to be positive. It is coming 8.8 degree. Same way as we are having our degree of reaction to be constant, and that too it is 0.5, we can say we will be having symmetrical blading. So it says my alpha 2 at the mid station and my beta 1 at the mid station, that's what is same, and it is 44.89 degree. We have our alpha 1m and beta 2m, that's what is coming to be same, and that's what is 8.8 degree. So just look at how you will be changing your velocity triangle. So this is what is my velocity triangle at the mid station. Okay, always repeatedly I am saying, make a habit of plotting the velocity triangle when you are doing your calculations. Okay, now at the tip station also, in line to what all we have discussed, we can do our calculation for CW1 and CW2 at the tip station. So this is what you can say my degree of reaction is 0.5. That's what is giving my CW2 at tip plus CW1 at the tip as some number. Same way, based on our work balance, we are getting CW2 at tip minus CW1 at tip as 18.92. Now based on that, we are able to calculate our CW2 and CW1 at tip station. Now as we have discussed, since my tip diameter, that's what is larger, so U value, that's what will be coming to be larger. We can do our calculation for beta 1, that's what we can have as a 47.29 degree. We have our alpha 1 as a 24.35 degree, and because of degree of reaction to be 50%, we will be having symmetrical blading. And for those symmetrical bladings, my alpha 2 and beta 1, that's what is coming 47.29 degree, and my beta 2 and alpha 1, they are coming say 24.35 degree. Okay. Now after doing all this calculation, here this is what is very important, that's what we need to observe. So this is what is representing the variation of my angle from hub, mid and tip station using free vortex concept, and this is what is with constant reaction concept. So here if you look at say my delta beta, if you are looking at for free vortex concept, we have discussed that's what will be coming to be large. Okay, and if we are looking at say variation of my delta beta, that's what is from hub to tip is coming larger, that's what is giving highly twisted blade. Remember, this is what is interpolation at particular 3 station, hub, mid and tip section. Now here for constant reaction, if you are comparing these angles are coming to be lower. Okay, and this is what is representing how my degree of reaction, that's what is varying. So this line, that's what is representing my free vortex concept, and this line, that's what is representing my 50% reaction concept. So if you try to compare these two, it says at mid section for free vortex, my degree of reaction is coming to be large, maybe around 0.65. Okay, and that's the reason why if you look at near the hub region, our degree of reaction is coming to be larger, maybe around 0.18. Okay, and if you compare both the design approaches, it says for free vortex design approximately at 30% span, your degree of reaction is coming 0.5. So I'm sure this is what will be giving you idea when we are taking two different approaches for our design. So we have discussed about this design approach, that's what is called free vortex design concept, and we have taken the approach, that's what is constant reaction design approach. Okay, so it is advisable that you do your pen paper calculation, literally sit down and do the calculation. That's what will give you more confidence in sense of doing the calculation for variation of my whirl velocity components, variation of my degree of reaction, variation of flow angles. Thank you very much for your attention.